Time flies. Believe it or not, episode 70 is already here, and I'm excited and surprised at the same time. What did you do for my past 70 episodes? Or the question should be, where did the time go? Well, in this particular case, the question should be, where does the time go actually? Or how does it ripple? Is it really a human concept now that we know that gravitational waves, which are caused by massive accelerating objects that disturbs the fabric of space-time, are real? Well, this is how the story goes. I'm quoting Michio Kaku now, mostly because of the simplicity of the model he describes. So children ask the question, if the moon goes around the earth and the earth goes around the sun, what does the sun goes around? And the answer is a black hole. Also, before we go any further, consider this. A black hole might hypothetically reveal its singularity if it spun faster than this limit, creating a quotation mark, naked singularity, a situation that is prohibited by general relativity since it would breach the event horizon and violate the cosmic censorship conjuncture. The equations of general relativity dictate a black hole's maximum spinning rate. The Kerr parameter, also known as the spin parameter or dimensionless spin, defines this, again, quotation marks, cosmic speed limit and goes from 0 or non-spinning to 1, maximally spinning. The event horizon of the black hole would be revolving at the speed of light at this top limit. So where are we then, you may ask yourself? Well, thanks to AI, we have more and more info. So it was Sagittarius A*, or the supermassive black hole at the center of the Milky Way, our home galaxy, which was measured for speed or spin using a Bayesian neural network, a type of artificial intelligence. Millions of synthetic simulations created with high-throughput computing capabilities from the Center for High-Throughput Computing, or CHTC, a partnership between the University of Wisconsin-Madison and the Morgridge Institute for Research, were used to train this neural network. Also, according to Scientific American today, we can detect the speed of the escaping material, the energy of the blast, the strength of the magnetic fields, and even the density of gas and dust that the outflow is flowing through. Furthermore, once the outflows leave the newly formed accretion disk, they can travel several light years in distance before they fade. Observing these outflows gives astronomers a unique way to probe the environment around the previously dormant supermassive black hole on a detailed level not possible with other methods. And we have one in the center of our own Milky Way galaxy, and we spin around it at speed estimated between 220 and 250 kilometers per second, or about 490,000 to 560,000 miles per hour. That is fast, you have to admit. Are you still asking yourself where does the time go, or how fast does the time really go? Because this is all about gravitational waves and time ripples. Maybe literally everything we and Spaghetti Monster knows how many civilizations besides us, before or after us, eventually all end up in one of infinite number of black holes. Fast, very, very fast. Names, faces, memories, possibilities. Does all the time in all the worlds eventually ends up in one of the most mysterious, I have to call it, entity, because it is scary. That's why I call it the entity. Or do we get a second, third, and whatnot other chances? And are our chances infinite? Not karmically infinite, just infinite, regardless of if they're good or bad or whatever. Whatever it is, and whoever it is near the spinning darkness cannot possibly end well. Fast, very fast. However, to a far outside observer, the situation is quite different. therefore no one would notice. The falling observer appears to slow down more and more as they get closer to the event horizon because of extreme gravitational time dilation. As the infalling person's light gets indefinitely redshifted, like that is like totally redshifted, and time dilation reaches infinity at the horizon, the outside observer would really never see them pass the event horizon. Instead, they would appear to freeze and fade away. In 2022, Event Horizon Telescope, or EHT team, released the famous picture of Sagittarius A asterisk at the center of the Milky Way, and it was only then we realized a black hole was really way more than pure speculation. Sure, it was predicted a long time ago, in a way. An intriguing conflict between theoretical prediction and individual doubt can be seen in Albert Einstein's interaction with the idea of black holes. Although Einstein's general theory of relativity from 1915 established the mathematical basis for black holes, he denied their actual existence for many years. As you may already understand, general relativity redefined gravity as space-time curvature caused by mass. Carl Schwarzschild's 1916 solution to Einstein's equation revealed the possibility of singularities, infinitely dense points now recognized as black hole cores. Well, okay, I won't bother you with that right now. So what was this thing all about? So it is like this. Dark matter halos and orbital dynamics, meaning, the gravitational environment is changed when a black hole has a dark matter halo surrounding. Research demonstrates that dark matter halos can alter the effective potential for matter and spinning particles and move the innermost stable circular orbit, or ICCO, closer to the event horizon, among other characteristics of orbits close to the black hole. Although the motion of matter around the black hole is the main effect, this can also indirectly alter the black hole's spin-up rate over time by influencing how effectively angular momentum is transferred to it. So, this, my friends, is where there might be an answer. A worldwide team of scientists detected the first ever mid-IR flare from Sagittarius A asterisk, the supermassive enormous black hole at the center of our home galaxy, Milky Way. We love Milky Way. That was earlier this year using the MIRI instrument aboard the James Webb Space Telescope. The scientists discovered the radio counterpart of the flare that was behind scheduled in simultaneous radio measurements. The mid-IR flare was accompanied by a radio flare that was identified 10 minutes behind the infrared incident. Scientists can better examine the physical processes and particle dynamics in the black hole's near surroundings thanks to this temporal lag. And you know how it is with Americans and Iranians. Americans either wage war or cooperate fantastically with Iranians. One of them, who fantastically cooperate with the United States, a renowned scientist, said flares are expected to happen in essentially all supermassive black holes, but our black hole is unique. That was Farhad Yousefzadeh, an astronomer and a professor of physics and astronomy at Northwestern University. He focuses on studying the physical processes that takes place in the Milky Way's nucleus. His primary areas of study include the galactic center, specifically Sagittarius A asterisk, and its environs, which include cosmic rays, flare activity, and star formation. And his associate as well, they observed Sagittarius A asterisk for a total of 48 hours in 8 to 10 hour intervals using Webb's NIRCam sensor. He also points out it is always bubbling with activity and never seems to reach a steady state. We observed Sagittarius A asterisk multiple times throughout 2023 and 2024, and we noticed changes in every observation. We saw something different each and every time, which is really remarkable. Nothing ever stayed the same. When you're looking at such weak flaring events, you have to compete with noise. If we can observe for 24 hours, then we can reduce the noise to see features that we were unable to see before. So, don't be surprised why the supermassive black hole at the center of our galaxy has recently been the subject of multiple studies, aiming to determine how fast is it spinning. And here are the latest findings. Well, researchers using machine learning and data from the Event Horizon Telescope have determined that the black hole is spinning at an exceptionally high rate, between 80 and 90% of the maximum possible speed for a black hole. And this so-called maximum is set up by Einstein's theory of relativity, which limits how fast a black hole can rotate before its event horizon would break down. The study leveraged AI trained on millions of simulated black holes to analyze the EHC data from 2017, providing the most precise estimate yet of Sagittarius A spin, which was previously determined to be around 60% of its theoretical maximum using radio and X-ray data from NSF's Very Large Array and NASA's Chandra X-ray Observatory. According to these findings, the fast spin is causing the surrounding spacetime to twist into the shape of a football and may eventually give neighboring matter a strong kick if additional stuff falls into the black hole. The high spin rate means that our black hole is dragging spacetime and nearby matter around at incredible speeds, influencing the dynamics of the galactic center. Also, according to MIT, Universe Today, and Spacecom recently, not so recent, data indicates that there might be less dark matter in the galactic core than previously thought, which defies the notion that dark matter is more concentrated in the Milky Way center. There is a more considerable dark matter halo in the outer regions, whereas the dark matter distribution seems to be more cored, with a lower density towards the center. Research in this field is ongoing and could result in changes to our knowledge of the function of dark matter in galaxy formation and structure. However, these are news from the beginning of 2024. And this stood in stark contrast to previous measurements that showed a hint of dark matter distribution since the 1970s also rotate at almost the same speed independent of their distance from the galactic center. This so-called flight rotation curve was surprising because these velocities could not be explained by the visible materials alone. The flatness of the curves was one of the most convincing arguments or the existence of dark matter. It is impossible to attribute the observed high velocities in the outer regions of galaxies to the apparent mass, so we say stars, gas, and dust alone, but the discrepancy suggests that the presence of dark matter, an unseen material that surrounds galaxies in a halo. So, the existence of dark matter, an invisible mass dispersed throughout the galaxy, particularly in its outer parts, was the only tenable explanation. And the idea that the galaxies are surrounded by dark matter halos was established by this groundbreaking study, which was headed by V.R. Rubin and colleagues. I don't know if you remember, but while working with Ken Ford in the late 1960s and 1970s, sensitive spectrograph to measure the velocity of stars in spiral galaxies, starting with the Andromeda Galaxy, or M31. Prior galaxies measurements revealed that stars were orbiting the core at a rather constant speed as they got farther away. Dark matter is the sole explanation for this. V.R. Rubin of the Carnegie Institution in Washington was the first to do this work, and other astronomers' numerous observations in the years that followed confirmed it. So to repeat and conclude, according to SciTech Daily, AI uncovers wild spin of the Milky Way's supermassive black hole. Its axis of rotation is oriented toward Earth, and the emission close to the black hole is primarily due to highly hot electrons in the surrounding accretion disk. It seems that the accretion disk's magnetic fields behave differently than is typical of disks of this type. Using millions of simulated models and artificial intelligence, a group of astronomers from around the world had discovered new information on black holes, particularly the one at the center of our own galaxy. So what they have found was that Sagittarius A asterisk at the center of the black hole of the center black hole of the Milky Way is spinning at almost its full speed, thanks to this state-of-the-art method. That's how they discovered it, right? And the researcher used a massive collection of artificial black hole simulations to train a neural network in order to achieve this accomplishment. The Center for High Throughput Computing, or CHTC, as I have said, is a collaboration between the University of Wisconsin-Madison and the Mordridge Institute for Research, provided the high throughput computing technology that enabled this. 3 new studies containing their techniques and findings were published in the journal Astronomy and Astrophysics. This stood in stark contrast to previous measurements from the 70s that showed a hint of dark matter distribution. Prior galaxies measurements revealed that stars were orbiting the core at a rather constant speed as they got further away. Okay, now stop for a second and remember what I said at the beginning of the episode about naked singularity. Okay, remember now? So you might ask, okay, we got it, so what's new? Well, apparently the SAG-A is in some serious trouble considering it is spinning almost out of control. So, okay, I'm exaggerating. It is not becoming rogue because I'm not talking about another black hole discovered in our galaxy some 5,000 light years away, with which, for the first time, astronomers have confirmed the existence of a lone black hole, one with no star orbiting it. That's nightmare. Can you imagine if that thing comes over here? Like, that would be a disaster. Well, we don't know. This black hole is much closer than the supermassive one at the Milky Way center, which also lies in the Sagittarius but about 27,000 light years from us. The black hole is about 7 times as massive as the Sun, give or take 0.8 solar masses, but this is not about the potentially rogue black hole. Back to SAG-A, back to possible naked singularity. I have to tell you what happened. A neural network has been trained using millions of artificial black hole data sets by a group of astronomers under the direction of Michael Janssen from Radboud University in the Netherlands. And among other things, they now estimate that our Milky Way's central black hole is whirling at almost peak speed. The first picture of a supermassive black hole in the core of the galaxy EP70 was published in 2019 by the Event Horizon Telescope collaboration. A little later, they also displayed a picture of SAG-A, the black hole in our Milky Way. That was in 2022, yeah. Nevertheless, there was still a lot of difficult to decipher information in the data behind the pictures. A neural network was trained by a global team of researchers to glean as much information as possible from the data. And this is all even before quantum computing, so this is fascinating, right? According to an article published at Phys.org, a lead researcher, Michael Janssen from Radboud University, pointed out that, quotation marks, now I'm quoting, that we are defying the prevailing theory is of course exciting. However, I see our AI and machine learning approach primarily as a first step. Next, we will improve and extend the associated models and simulations. And when the Africa Millimeter Telescope, which is under construction, joins in with data collection, we will get even better information to validate the general theory of relativity for supermassive compact objects with a high precision. And for you unfamiliar with the AMT, this is what it is. On Namibia's Gamsberg Mountain, a 15-meter single-dish radio telescope known as the Africa Millimeter Telescope, or AMT, is planned. The area is renowned for its exceptionally clear skies and minimal light pollution, making it an excellent site for astronomical observations. Since the 1970s, the top has been home to a small astronomical observatory run by the Max Planck Institute, and I'm pretty sure they don't need no introduction. So, about the location. It is intended to be a vital news station in the worldwide Event Horizon Telescope, or EHT network, which photographs supermassive black holes like SAG-A at the Milky Way center. It will function at millimeter wavelengths, and the AMT will be Africa's first millimeter wave radio telescope and will considerably boost the EHT's imaging capabilities by filling a geographic gap in the southern hemisphere, improving the area's resolution and durability as well. The telescope will be a refurbished 15-meter dish, originally the Swedish SO sub-millimeter telescope or SEST, donated by the European Southern Observatory and the Onsala Space Observatory. It will be equipped with receivers operating at different frequencies. Only a few realistic synthetic data files were employed in earlier research conducted by the Event Horizon Telescope collaboration. This time, the astronomers input a Bayesian neural network which is capable of quantifying uncertainties, millions of these data files. And this made it possible for the researchers to compare the models with DHT data considerably more effectively. The researchers did not just make predictions about SAG-A, they also looked at M87, the black hole at the center of M87 galaxy. And I'm pretty sure you all remember that black hole, which has a mass of about 6.5 billion times that of the Sun. Yeah, you heard that right. You heard it right. This tiny little black speck was the first we took a picture of. I don't know why. Maybe was it because it was so big, or I have no idea. It is a supermassive black hole located at the center of the galaxy Messier 87 or M87, about 55 million light years from Earth. It was the first black hole to be directly imaged by the Event Horizon Telescope collaboration with the iconic image released again, like as I have said, in April of 2019. Unlike SAG-A, it is this galaxy is spinning in the opposite direction to the infalling gas. The astronomers suggest that this rotating motion may be the result of a merger with another galaxy a long time ago. And this is why is it important. And I'm quoting now my previous sources. Measuring the spin of SAG-A allows scientists to test predictions of Einstein's general relativity in the extreme gravity regime near a supermassive black hole. The spin rate influences the shape of the event horizon and the behavior of space-time around the black hole, providing a direct probe of fundamental physics. The spin of a black hole is closely tied to how it accretes matter and produces energetic flares. Recent multi-wavelength observations, including the first mid-infrared flare, have helped fill crucial gaps in understanding how magnetic reconnection and synchrotron emission power these flares. Knowing the spin helps refine models of how energy is released and transferred into the accretion disk and how electrons are accelerated to near light speeds. The new findings link previously disconnected observations in radio, submillimeter, infrared, and X-ray bands, revealing how the black hole's spin and magnetic environment give rise to rapid multi-wavelength variability. The spin rate encodes information about a black hole's history, how it has grown by accreting matter or merging with other black holes. High spin rates suggest prolonged, coherent accretion or major mergers, while lower spins might indicate more chaotic growth. This helps astrophysicists reconstruct the evolutionary path of SAG-A and other supermassive black holes. And I must state this without exaggeration. A key finding for black hole astrophysics, the new measurement of SAG-A speed advances our knowledge of basic physics, accretion processes, and the dynamic environment of our galaxy center. It closes long-standing theoretical and observational gaps and paves the way for future research on the universe's most extreme objects. What the future holds, of course, nobody knows, but significant advancements in black hole exploration and are anticipated over the course of the next 10 years, propelled by cutting-edge scientific methods, ambitious missions, and new technologies. The next Event Horizon Explorer will try to increase image sharpness by a factor of 10 after the Event Horizon Telescope captured the first ever image of a black hole. And this could give researchers clear proof of black hole spin and the way it distorts space-time by enabling them to see photon rings, which are thin rings of light formed by photons orbiting the black hole. If and when found, these photon rings would provide rock-solid observations of how revolving black holes affect light, which would help us better comprehend general relativity. A novel method of measuring black hole spin, particularly in low luminosity active black holes that are prevalent across the cosmos, and previously unattainable views of black hole jets, will soon be possible thanks to upgraded interferometers and next-generation telescopes. New information regarding the spin and evolution of black holes is being revealed via X-ray polarimetry, which has already been improved by missions like NASA's IXPE and ISRO's XPOSat. It is anticipated that these radio and X-ray observations will continue to be at the forefront of black hole research, offering vital information on their basic characteristics. The first space-based gravitational wave observatory that can detect low-frequency waves from supermassive black hole mergers is the planned LISA mission, which will provide a fresh perspective on the development and evolution of black holes, particularly the largest and most distant one. And this is particularly interesting in the light of this episode. According to recent studies, supermassive black holes that spin quickly may serve as natural particle accelerators, offering clues about dark matter and other fundamental particles. Observatories like IceCube and the Kilometer Cube Neutrino Telescope might detect high-energy particles emitted from these cosmic events, complementing data from Earth-based supercolliders. Though theoretical research continues to examine these possibilities for the far future, the idea of using black holes as energy sources is still firmly in the domain of science fiction, mostly due to the enormous technical obstacles and great distances involved. So, further research for sure. There's more to learn. If you have time, and you should find some because it is not infinite, look into the work of previously mentioned Michael Janssen, but also don't hesitate to check work and research of, for instance, Primayata Natarajan, an astronomer at Yale University, and she has significantly advanced our knowledge of supermassive black holes, dark matter, and their development. She's a fellow of several important scientific societies, has won multiple significant honors, including the Danny Heinemann Prize in Astrophysics in 2025, and is renowned for her groundbreaking work in gravitational lensing and black hole assembly. And that's actually super interesting. Also, Warren R. Brown, astrophysicist at the Smithsonian Astrophysical Observatory. Brown has contributed to the study of black holes in dwarf galaxies and the dynamics of hypervelocity stars, helping confirm the existence of supermassive black holes in nearby galaxies. And before we go, who else? Ragadepika Pucha, a postdoctoral researcher at the University of Utah. Pucha led a team that compiled the largest sample of dwarf galaxies hosting black holes, expanding our understanding of black hole populations and their role in galaxy evolution. And the list goes on, but this is good for a start. So, it seems that black holes can have indigestion and spit forth material years after the original stars were torn apart, which is a startling development that was not anticipated by theory, and I kept it for the end just as a fun fact for the end, or before the end. And the equivalent of this cosmic burp, scientists are now discovering that up to half of black holes that consume stars reappear in radio light years after they had previously gone silent. Crazy, right? And you know what? From Event Horizon to Interstellar, the fascination with black holes are many. Black holes are frequently interpreted symbolically as standing for deep unknowns, finality, and the boundaries of human comprehension. Concepts that are strongly associated with existential anxiety, which is characterized by feelings of uncertainty, meaninglessness, and confrontation with the emptiness. Well, once spaghettified, there is no hope for your body or soul either. Time flies, and time will tell, especially if you live long enough. We are not going to exist that long, and eventually everything we ever knew will vanish. And we probably will eventually hit the black hole, every piece of information will be irreversibly destroyed, and no strong faith or whatever grounds you will help. Black holes are not only spinning rotors of our galaxies, but also the one who have the upper hand over everything and anything. You can pray, but if you do, Make sure you pray to great nothingness, because this is where we all go even before we absolutely freeze. And then, what's the point? Whatever you choose, the selection of your destiny will be final. But until then, and still, stay selective. Bye-bye.